Hey students, this is part 2 of our first lesson of chapter 5a. And before I get into the lesson, which is about geometric sequences, I want to talk just a minute about effective note-taking. As you know, we've gotten to the end of the first 2 chapters. The main issue I've heard from students about the videos is that the videos they're just not meaningful for them, that they aren't learning from the videos. The one thing I can say is, and I'm not sure this is for everybody, like big balloon, umbrella statement, is that I would suspect that if the videos aren't useful for you, that means that you are not doing the examples, and maybe you're also not writing down the main ideas. I'm not really sure. But I think for effective note-taking for these particular lessons, I try to keep my personal writing down to a minimum. But if I were you, I would always make sure that you write down the main ideas, whatever those main ideas are. If I give you a formula, put down that formula. If the main idea is a parent graph, putting the parent graph down on paper so you have evidence of it. And then also, if you ever raise a question with me, I can look back at those notes and be like, oh, check out that main idea. That's what we're going to talk about right now. And having evidence of the main ideas is helpful for practice. But if you're watching a lesson at 8 p.m. and you're not going to see that practice again until like 11 a.m. the next morning, just watching me do the examples and expecting your brain to remember those examples 8-9 hours later without writing anything down, I think that's a pretty unrealistic goal. It's just me speaking from my own personal experience, but if you watch something on television or something, 10-11 hours later, you don't remember all the details about it. You might remember the main idea, the big picture, but there's little details, and those details might get skipped over on you. So I strongly recommend, and this is, I'm really going to start bugging people about this, is doing all the examples. Now, in a traditional classroom, when you're taking notes, you are expected to, write the notes into your notebook, the examples into your notebook. And during a lesson, the only thing that you could do is you could work on the examples during the teacher working on the examples. You and the teacher working on the examples at the exact same time. One reason I'm doing these video lessons this year is maybe doing the examples with the teacher while the teacher is doing them isn't best effective for you. Maybe you're able to look at the problem and solve it before I even solve it. So in which case, if you know how to do the problem, pause the video, do the problem on your own, and then play the video and make sure that you're doing it right. That seems like an effective technique if you know how to do the example. If you don't know how to do the example, but you think you might know how to do it, you could always work on the example during at the same time. And if you get behind a little bit, you could pause it, get caught up, but just do the problems at the same time, kind of like traditional note-taking. And then the third way is, let's say you look at the example and you're like, I don't know how to do that example. Well, just spend a couple minutes, watch me do the example, then pause the video and do the example afterwards. If you could watch me do an example and then you pause the video and you're able to do that exact same problem flawlessly, that's showing some learning. It's showing that you're understanding a little bit of that main idea. And then your notebook will also have an example of a correctly solved out problem. So when you start that practice the next day, you're not so confused. So anyway, and just once again, write down all the main ideas and do all of the examples either before I do them, while I do them, or after I do them. And that's the beauty of these video lessons, is you can do these examples whenever you want. All right. That investigation that we solved, multiplying to get from number to number to number to number, that is an example of a geometric sequence when we multiply to get from number to number to number. And I have 4 examples here for you. And in terms of writing down notes, I'm going to show you all 4 examples beforehand. These are the 4 examples I'd like to do. we're going to take these 4 examples and we're going to find the common ratio. We're going to have to answer whether it's a growth or decay. We need to find the percent change. And that's what we're going to do the first time around. And then second time around, we're going to make recursive formulas for numbers 2 and 4. So if you think you know how to do these examples, pause it, work the examples, and then play the video again and make sure that you did them right. Or do the examples with me right now. But at the very least, go get yourself some paper and pencil and write these 3 examples down so that you have them there for your note taking. So if you're going to solve these before, you should pause right now, start solving it. If you're going to do it with me, let's start working it. Common ratio. What are we multiplying the first number by to achieve the second number? And in this one, I think it's pretty obvious. 3 times what is 6? 6 times what is 12? What we are doing is we're multiplying by 2. Well, how do we use the 6 and the 3, or how do we use the 12 and the 6 to get this answer of 2? Well, 6 divided by 3 is 2. 12 divided by 6 is 2. Or, let me just put some words into this. How I'm going to view it is that you could view it as the current number divided by the previous number. Or you could think of it as the, just different wording of it, the next number divided by the current number. So in this example, let's say that my current number is 3. If my current number is 3, my next number is 6, and 6 divided by 3 is 2. And you could always check it. It should be, consistent. 3 times 2 is 6. 6 times 2 is 12. So 2 is that common ratio. Part 2. Is this a growth or a decay? If the numbers are getting bigger, it's a growth. If the numbers are getting smaller, it's a decay. 3, 6, 12, bigger, 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 growth. Then, percent change. How are we going to do percent change? Well, if you just change, if you were at 3 and then you're at 6, how much of a percent change is that? That's 100%, because 100% of 3 is 3. 100% of 3 is 3. So if we added 100% onto 3, we'd end up with 6. 100% of 6 is 6, and if you added that 100% to that 6, you'd end up with 12. So the percent change in this particular case is 100%. But how could you use our common ratio and percents to figure out your percent change? What I'm going to teach you is this, that if it's a growth, you could find this out by going the common ratio minus 1, and then answering as a percent. So in this case, the common ratio is 2. 2 minus 1 is 1, and then 1 as a percent is 100%. Okay, so I used a simple example to teach myself how to solve a more complicated example, such as this one. Let's say I had 10, 12, 15.625, and so on. Let me get a new piece of paper for this so we aren't getting confused. So if I look up to here, based off what I learned in the previous example, going the next number divided by the current number or 12.5 divided by 10 will get you your common ratio. I shouldn't need a calculator for this. It's going to be 1.25. You get 1.25. But you want to make sure it's a geometric sequence, so keep going with that. Go 12.5 times 1.25. You should get 15.625, and I did. And if I multiply by another 1.25, I do get that next number. So this common ratio of 1.25 seems to be sticking. Growth or decay. Numbers are getting bigger, growth. Part 3, the percent change. The common ratio minus 1, 1.25 minus 1 is 0.25, but we're looking for percent change, so we change that decimal to a percent, and you get 25%. So each number is increasing by 25%. All right, let's look at some problems that are getting smaller. 100, 70, 49, 34.3. Well, common ratio, same thing. Previous number divided by the current number, 70 divided by 100 gives you 0.7. And if you go 70 times 0.7, you will get 49. 49 times 0.7 is 34.3. So we have a geometric series with a common ratio of 0.7. Part 2, these numbers are getting smaller, so we're talking about a decay. And then finally, part 3, percent change. Well, if it's a growth, we go common ratio minus 1. But if I do that, 0.7 minus 1 is negative 0.3. And you wouldn't say a negative 30% change. What you'd say is you'd say a 30% change. Because it is. Like if you went from 100% down to 70%, that is a 30% change. It's just a loss. So in a decay, you do the exact opposite. Instead of going the common ratio minus 1, you go 1 minus the common ratio. So in this case, 1 minus 0.7 is 0.3. We change that to a percent, it's 30%, which that kind of makes sense. If you were at 100%, but then you had a 30% discount, you'd then be paying 70%. I'd change that to a test to a discount. Anyway, 100 down to 70, 30% discount, 30% change. I get those confused. So this was me using an easier example to explain a difficult problem. So my last example, number 4. And this one, it's a little less recognizable, but use the same ideas. 51.2 divided by 128 is a 0.4. And then if you just want to check, because it sure doesn't seem like this would work out, if you went 51.2 times 0.4, you do get that 20.48. You take that and multiply it by 0.4, you get the 8.192. It's checking out. So that's part 1. Part 2, the numbers are getting smaller, so it is a decay. And then finally, number 3, 1 minus the common ratio. 1 minus 0.4 is 0.6. So what we have is a 60% change. Sorry about that, I lost the bottom of the paper here. 60% change. Okay, so that is just common ratio, growth and decay, and percent change. And this is what you'd want to memorize with that. The next thing that they're asking us to do is write a recursive formula for number 2 and 4. So if I brought out number 2, looked like this with that common ratio of 1.25 and a first number of 10. For a reason I will explain at a future date, you're going to want to start all these problems with U0. U0 is this first number, which is 10. And then to get from one number to the next, you are taking that previous number and you're multiplying it by that common ratio of 1.25 with n greater than or equal to 1. That'd be the recursive formula for number 2. And then if I did a recursive formula for number 4, in that case, u0 is that first number, and u0 is, so I guess is 128. And then the next number is you're taking that un minus 1 and multiplying it by the, what do you multiply it by? You multiply it by the common ratio, 0.4, with n greater than or equal to 1. So that is a recursive formula of a geometric series. Okay, so those were the 4 examples. And like I said, everybody, you need to work through these examples. Watching Mr. Elliott do math examples will not help you get better at math. Actively practicing math problems will get you better at them. So if you've not yet tried these problems out, you've now watched Elliott solve them, now try them on yourself. Try them out yourself. Try out these 4 problems, or 5 if you can include these, and then make sure you can get the same answer as I did. And if you can pull these problems off flawlessly, then tomorrow when you get to the practice, it won't be a problem at all. So anyway, I hope you all have yourselves a great Tuesday or Wednesday evening, and I will see you on Thursday for our practice with geometric sequences. Bye-bye, everybody.